don't know much about him, but even maybe I'm writing it. I think it's pronounced Galois. Do you know him? Can we read actually from Wikipedia? By the way, we have Wikipedia at Bilkent. That's fun. French mathematicians, while still in his teens, he was able to determine a necessary and sufficient condition for a polynomial to be solvable by radicals, thereby solving a problem standing for 350 years. What have you done with your teens? But never mind, it ends sadly. These violent delights have violent ends. His work laid the foundation for Galois theory and group theory, two major branches of abstract algebra, and the subfield of Galois connections. He died at age 20 from wounds suffered in a duel.
I didn't die in a duel in my teens. That's my
accomplishment. That's your accomplishment. Yeah, you keep burning oxygen. My son realized that every time I laugh, I cough afterwards. You find that correlation. Okay, so let's talk about group theory, okay? And I don't know a rigorous way to talk about it, but it's about operations. Like, let's imagine an operation A and operation E, okay? If I operate A twice, let's say, it is E. And if I operate E on A, it's A, let's say. AE is A. Why the thing is running so? I don't know. But anyways, A and EE is E. So can you tell me what E is? It's the identity operator. Whenever it hits something, it gives whatever it hit. Do you see? Just there E is not hitting anyone. Okay. Okay. Yes. Okay. Let's draw a table. Like E times E. Do you know the multiplication table? E. E times A, E. Okay? This is a group. And a group needs one identity operator. Yes, exactly. Because if it's A, it doesn't sound fun. I don't know. I think... Okay. Let me... I mean, it has to be self-consistent. So there are two things. It will either be E or A. What do you want it to be? A? Like A squared, do you want it to be A?
I don't understand. It's normally in group theory we don't.
What?
For example, numeric numbers are a group.
Numbers are a group. Yes, very good. Let's start from there. But it's a different group. This is a different group. So this will be corresponding to some kind of group. Okay, and actually, yeah. I'm making up a group. Okay, is there something wrong with it? Uh, One thing that we should be careful about is that the group needs identity operator. Okay, that's for sure. I remember that, but I don't remember many other things. And there is a representation for them, like called irreducible representation. So it turns out that whatever group you can think of, there is a way of relating them to actual numbers and multiplication. Okay? In this case, if you set e to 1 and a to minus 1, do you see? You will get all the operations correctly. So e times e is 1 times 1, which is 1, which is e. Do you agree? A times a minus 1 times minus 1, 1, which is e, etc. You are not happy? Okay. Sometimes it doesn't work. Like sometimes there are things like AB is C, but BA is D. Okay. How would you represent then? A, B, C. Would you still use numbers or something else? You will use matrices so that multiplication gives you different things. So after doing one semester work, you will arrive at character table. Okay, for each symmetry group there is a character table, and let me actually, this website is super awesome. So it will give you all the groups, character tables for chemically important point groups, and it would explain you what a group means, what it is all about. What it has to do with today's class at all. I want to study my system, my molecule, and its vibrational modes. Okay? That's what it has to do with that. And here, since all atoms are equivalent, it turns out that this molecule corresponds to D3H group. Okay, what this D3H group means? Remember, you had operations like E and A. This time you have operations like symmetry operations. For example, you have C3, which means that rotate it in this direction with 120 degrees, it will fold on top of itself, right? You have you have another C3, so you have two C3s. Are you following? Which would operate this one in the opposite direction. Okay? So for example, what is C3 times C3 times C3? What operator is it? It's identity, right? So it's identity, E. Now, as I'm telling you this, it starts coming back to me. So basically, it's for these particular groups, you can write down all the operations. Like there is identity, there is C3, there can be C3 prime, which will be the rotation in the opposite direction. So you can just fill this in like this. And for example, there's C3, C3 prime. What is, for example, this? C3 times C3 prime. Yes. So you see, you know group theory now. And if you go to representations, and in this case, you will actually need matrices at some point. And I will tell you why I know that you will need matrices in a moment. So there are other operations. For example, let's go to D3H group. And over here you would see operations. Like there is one E, there are two C3s. Do you remember them? One this way, one the other way. There are three C2s. C2. What is C2? 180 degrees of rotation. And how can you operate on this? 1, 2, 3. And for example, there is one C2 over here. I'm very sorry. So 1, 2, 3. There is one C2 over here that would flip it. And you would get 1, 3, 2. But it wouldn't matter because they are the same things, right? Do you see? So then over here there is C2, 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 different kinds of C2s. Why there are three of them? Because you have this axis, and this axis. Is it forming in your mind somehow? Good. Let's go to other operations. For example, there is this sigma h, which is reflection. When you have sigma, it's reflection. And h means, I think, with respect to horizontal plane. So basically, 1, 2, 3. 1, 2, 3, right? And if it was like pointing up, it's not, but I just want to show you something. Take the mirror symmetry, right? Then they will point down. Do you understand what's going on? Everyone? Yes? Okay. Why Mac is so hot? I don't know. Do you hear the sound? Something is running, but I don't know what. Anyways. Yeah, of course. I don't mind that. So, what else? There's this F3, which is rotate and then take the mirror reflection. Okay, it's complicated a little bit. And then there is this mirror symmetry, which is like there are again three axes. Remember we did C2s. Sigma V's are different. They actually are reflecting. So, for example, can I give a nice example for this? Okay, for example, if they are like this, okay, and I apply C2, then I will get this one because I'm actually flipping the thing, okay? This is what you get from C2. But if I apply at the same axis sigma V, then I'm actually taking reflection with this axis, which means that I will get this one again. Do you understand this point? No. Let me restate it. Do you understand this one? It's flipping. But sigma h is taking mirror symmetry with respect to this axis. Okay? So if you are up here, then you will go here, but you will still be up. It's just taking the mirror symmetry. Are you following? Everyone? It turns out that we can actually characterize our vibrational modes using this character table. Okay? How we can do that? Let's do it again. So the first mode, do you remember it? It was this one. Let's find out what is the corresponding irreducible representation? How can I find it? I will choose one of these operations. I will operate on this system and see where it goes. Okay. So identity gives you not so much information. This one is quite distinguishing. Do you see that? So if I apply C2 to this system, what do I get? So you have vectors like this. Apply C2. Then this arrow goes here, this arrow goes here. So they go to the same places, right? And if you multiply them, you will get 1. I forgot to mention that vectors are normalized here. Like if you take the prime of this one with itself, then you get 1. Do you remember the vectors, eigenvectors? But if you multiply it with something different, you will get 0. So they are forming orthonormal basis set. Thank you. So what is the value that I get applying C2? +1, yes? So it's either A1, do you see? Either A1 or A1 double prime, okay? Then how I can distinguish them? I can use this operation because it's 1 or -1. So if they are both 1, then I will definitely be A1. Let's do that for this one. Now, are you following? Please tell me that you are following. Yes? So let me take reflection with respect to this mirror. Then this one will go actually here. This one will go here. This one will stay there. So multiplication gives you 1. Then it's A1 group. Why does it matter? It matters a lot because from these other things that are written here, you can actually say that this mode, this vibrational mode, will be Raman active. You will see this in Raman measurement. Can you believe it? From Galois to material science. Right? And what about these ones? So let's plot number 2. Okay, sorry. Let's plot it again. What about this one? What is the group? Can you do sigma h to this? Like let's do it with respect to this. Then this one will go here. So you will get 1, right? And also you will get 1 if you flip it. So this is also Raman active mode. Do you understand my point? Or not? Hmm? No. If you get both of them 1, it means that it corresponds to this irreducible representation, which in turn is Raman active. For example, I'm not sure if it's Raman active or not, but you need to look at this function. I believe if it's quadratic, then it's Raman active. And these values, actually, if you don't have 1 here, then it means that you had to actually use matrices. And these are the dimensions of those matrices. Okay? Do you see how much information there is in one table? And it doesn't end there. It also gives you that if there is a state corresponding to this irreducible representation, it has to have a pair with the same energy. You have to have a doubly degenerate state. You understand? So the symmetry in the system gives you the degeneracies. Do you know that word, by the way? Degeneracy? Oh, sorry. Same energy, different states. Like, for example, okay, I will not give that example here. Let me go further and show you this one. In this case, I have 4 atoms that are arranged in a pyramid. Okay? Why not? And it turns out that, again, this website is super cool. Turns out that it corresponds to this table, and they even give the chemicals, and they even give the rotated animations. What else do you want, right? So do you see that our molecule will have the same geometry with this? You can ignore this one because it's right at the center. It has all the symmetries on the world. Okay, now that you know group theory, can you tell me what kind of degeneracies you expect from this system to have? Are you lost? Did I lose you? Hmm? No. I mean, for example, do you expect quadruply degenerate states? Like 4 states that have the same energy. Are you expecting that kind of states? It could be, but if it is there, it's only because of accidents. Normally, group theory tells you that you can have either non-degenerate states, ones and ones, double degenerate states, or triple degenerate states. If you have more than this, then they are just there because of some accidental, some other symmetry in the system. Are you following, everyone? Let me see. So let me show you the results for this one. For example, let's see the first state. It's actually doing the walls. Do you see it? It's doing this motion. That's one of the modes. There are many other modes. So let me open actually for number 4. Let's look at number 1 again. By the way, how many modes do you expect from this object? I totally lost you.
This is 3-dimensional.
This is 3-dimensional now.
3 translations. And then what would be the
No, think of the number of atoms. 12. Number of atoms times number of degrees of freedom, 4 times 3, 12. Okay? So the first mode is this one. Maybe I should be drawing with less. So let me take it to 1/3. So the first one you saw, do you remember? Do you see the symmetry here? So probably it corresponds to this A1 because I'm expecting every operation to be going there. But let's look at the eigenvalues. So this one has -4, and then there are this -2, -2, -2. Do you see? Were you expecting this? Yes, you were, because there are triply degenerate states, right? Come on, guys. Let's look at number 2. Let's look at number 2. I was planning to do much more than this, but I think I will not be able to complete it. So let's look how it looks like. Do you like it? So we need to figure out, we don't need, but we might want to figure out which one of these, is it T1 or T2? How can you do it? You either do this operation or you do this operation. Which one do you want to do? Actually, this sounds to me complicated. We can just not do it, right? Let me see over here. So there is -1 and -1. Were you expecting this? Yes, you were expecting this. Thank you. And without even operations, without doing any operations, you know which group that is, right? It's this one, right? It's this one. And let's actually see this by doing C3. It has to yield -1, right? Let's choose one of them. It's fifth mode, for example. Let's choose fifth mode. And it's something like this. And if you look at it from some point, you will see the symmetry. So if I rotate it with C3, well, it's not very clear, right? Let's look at others, like number 6, like the other one. What? Can you repeat?
It meant 8 C3. So we did C3 8 times, right? That's what it meant.
No, it means that you have 8 C3 axes. Okay. Just it's not as clear as the others. So, but trust me that this one will go to -1. Just let me show you that this arrow will, if you rotate it, it will come here in the opposite direction. Do you see? Although this one will go in the same direction, not in the same, but in this direction, etc. If you sum all that, I mean, after rotation, if you multiply them and sum them, you will get -1. Do you trust me? Yes, you do. What about other modes? So these are all 0. So you have 6 0 modes. Were you expecting this? Huh? 3 translation, 3 rotation. Do you see? Magic. Very good. So do you feel like you are much more comfortable with group theory now?
So you looked at one of the toughest applications of
What?
group theory. You explained group theory, and you applied it directly to atoms.
And
That was one of the more complicated, advanced examples of group theory. I mean, this numbers example would have been much simpler. You explained group theory.
I think I got too much used to it. I was planning to go further, but I feel like I lost you. Did I?
The details are unclear, but the idea is like it's not. For example, if you go from 2 atoms to 3 atoms, it's not exactly same line of thoughts. It just adds up exponentially. If you, for example, add 4 atoms, it becomes hugely more complicated. There is multiple items. Even people who are working in this, for example, if you go from one lattice to another lattice, you need to open books again, understand it again. It's just for right classes.
Okay. Because I was going to go to infinite atoms now. I'm not kidding. I'm actually was going to talk about these chains that go to infinity and how to deal with them. But maybe next time. Let's do it the other time so that because I will build on that later on. Thank you very much for coming.